We've seen some examples of Laplace transforms, and we also learned a few of the properties. Now the question is, what if somebody told you a Laplace transform of a function and told you to find the original function which produced the Laplace transform? That is called finding an inverse Laplace transform. So how to do it? So let's say somebody gave you a Laplace transform and asked you to find the original function. And to do it, we say that we apply an inverse Laplace transform to find the original function which produced that Laplace transform. So if the Laplace transform depends on S, then an inverse Laplace transform will depend on time variable. So we go from S domain to time domain, backwards. Now the best thing to do is to use tables of Laplace transforms. The reason for that is because you already spent time understanding how to get from a function to a Laplace transform, so why not just save the time and go backwards? So if you look at the right column of that table, you'll see Laplace transforms which depend on S variable in S domain, and all you need to do is to find a corresponding function in the left column, and that will be the original function corresponding to that Laplace transform. And also linear property, which we've seen in the previous video, also applies here. So if you have a combination of Laplace transforms, linear combination, then we can use a linear combination of inverse Laplace transforms, which you'll see in a moment as an example. Before we start, a small comment here. There is actually a formula which you can use to explicitly compute the inverse Laplace transform, like you do for the direct Laplace transform. But that formula would require maths which is well beyond the course unit we consider here, and more importantly, it's rarely used in practice because it's cumbersome and using the tables is much more efficient. But there are some rare situations where it might be needed, but let's just have a very quick look at it. So if you had a Laplace transform of a function, you remember that this is an integral taken with respect to time. Now the inverse Laplace transform involves so-called Fourier-Merlin or Bomovich integral, and this is the inverse Laplace transform integral, and it's -1, right? Notation which we used. So we use a formula to find inverse Laplace transform, which is looking like that. And I on top, in bottom limit, is the imaginary number, a complex number. And the integration happens with respect to S, which is in general can be a complex number. So I squared equals to -1, and gamma is just a real number chosen in a special way so that that integral can be computed. So that is the inverse Laplace by formula, which will produce the original function f of t. But the good news, again, you do not have to memorize that formula and you do not have to use it. So the only reason why I showed you this formula is to explain that it's much more difficult to do it directly instead of using a table of Laplace transforms. Let's look at the example. Example 1 is try to find a Laplace transform of that function. Example 2 is to find a Laplace transform of another function. Of all of them depend on S, right? Inverse transform applies only to the S domain. And then another fraction. Okay, and let's start one by one. So first what we do, we notice that a Laplace transform of exponent will lead us to this expression, and therefore the inverse Laplace transform will lead us backwards. And indeed, that's what we have. So all we need to do is just to go to the table, look closely at the expression and say, hey, that's just the exponential, and write it down. So that is the answer. Now the case B, somewhat similar, but we need to think of what is the inverse Laplace transform of the inverse squared of S. And that will be just a linear function. So the answer here will be that we need to get our inverse Laplace transform in a way that involves that function. That is, we take a factor outside that inverse Laplace transform. So this is a linearity. And then we can apply the inverse Laplace transform and get the answer. And a final example, let's just look a little bit more detail here. So we are asked to find an inverse Laplace transform for this fraction. So what we can do is we can say, remember that a Laplace transform of a cosine omega t is S over S squared plus omega squared. So the question is, can we guess what is omega here? And the answer is that omega is, I guess you already guessed it's 2. So 4 is omega squared, therefore omega is 2. But we also have the factor 12 here, which is not in the table. And again, using a linear property, we take it outside our transform. And here we go. We can write that a inverse Laplace transform of that function is 12 times inverse Laplace transform of S over S squared plus 4, which is 12 inverse Laplace transform of S squared plus 2 squared, and that is 12 cosine 2t, and that is the answer. So this is how you find inverse Laplace transforms using the tables of Laplace transform.